Hi everyone, today we are exploring a part of this paper, Machine Learning Augmented Branch and Bound for Mixed Integer Linear Programming by Lara and others. So this paper discusses how machine learning can be applied to various components of MIP solvers. And in this video, we will specifically focus on ML-augmented primal heuristics, and I'll cover the other components in the future videos. If you are new here, welcome back to the Reading Club. This is an ongoing series where I read papers on mixed integer programming and discuss their key ideas in simple language. So in today's video, we are focusing on ML augmented primal heuristics. In particularly, we will talk about three things. One, how ML can be used to predict solution values directly without using any heuristics at all. Two is that we are going to see how machine learning can help with finding better neighborhoods for a given solution in order to improve that solution. And finally, we will talk about how machine learning can be used for scheduling the existing heuristics in MIP solver. So let's get started. So the main job for primal heuristic is to find good quality solutions. So basically we can use ML for directly predicting the solutions. So this is now divided into two parts. So first is that how do we find good quality solutions, and then if the solutions are not feasible, which is most of the time because we are trying to predict it, we are not really solving any mixed integer programs for that. So since they are not feasible, then how do we make use of something that is not feasible or something that is feasible but may not be optimal? So let's talk about first how do we find the solutions. So let's say that we have a bunch of solutions available to us, right? So let's say we have these solutions and we want to find a higher quality solution. So let's say that this is feasible but may not be optimal. So we have solutions, but we don't know if they are optimal. We are looking for a better quality solutions. So most of the work about predicting solution was actually focused on binary variables. Why? Because for most of the problems, even in MIPLib, we have mixed binary problems or pure binary problems, or even when we are looking at general integer problems, the binary variables make up a big part of those programs as well. So the focus is purely right now on binary variables, and probably some of this work can actually be extended to general integer variables as well. So for the binary variables, the goal is that we want to find a probability that a certain binary variable can take the value 1. So that's what we are trying to learn. So there are many ways in which that can be learned. So first is by Ding and others in 2020. So this paper came up with this kind of a probability, target probabilities. So that is, let's just say that particular variable xj that should take the value 1 given this distribution. Like this set of solutions, let's say this capital X. So what is this probability? That probability will be equal to 1 if in all of these solutions, this variable takes the value 1, right? So the formal way of writing would be something like that. So this is pretty simple. Like, so if all of these solutions agree that this particular variable should be equal to 1, then we basically set it to 1, we fix it to 1. The other variables, we just simply ignore it. We don't fix it to anything. We can just compute a partial solution for now. Another approach is by Khalil and others in 2022. So they basically did something simple. They also say that the probability of this variable xj taking the value 1 given this data set x is simply just the average of how many of these people are taking this value. So the way to write it will be something like this. So this is slightly better than this one because this one actually gives some non-zero probability if not all of these solutions agree that this variable should be equal to 1. Okay, and note that these are feasible solutions. They are not necessarily optimal solutions. So some of these solutions might be of bad quality. So that's the part that needs to be fixed, that none of these two approaches take the objective into account. Like, so they are basically looking at the variable assignments, but they are not checking how good these solutions are. So to fix that, we have one more approach, which is by Vinod Nair and others in 2020. So they look at this kind of a probability distribution for solutions itself, right? So not just a solution variable taking particular value, but rather this entire solution, something like this. So we are now evaluating what is the probability for this particular solution, right? So we are associating some number for each of this solution, and it is something like this. So what is this number? So it is basically saying e raised to, this is C transpose X hat, which is basically saying that what is the objective value for this solution. And same thing here for all the other solutions as well. So this is in a way some sort of a softmax function, right? So the solutions which has the better objective value will have this number which will be closer to 1, and for the other ones which will be very kind of lower numbers, right? So closer to 0. So this is like some probability distribution. So this is not a complete probability distribution. It is just assigning numbers to this solutions as only. So they basically use a neural network to approximate this function, and they basically train this kind of a p theta function, right? So this probability theta function. And finally, they use all of this kind of probabilities to generate new solutions. So this one is pretty simple. Like, so if the probability is 1, then we can just simply fix it to 1, and otherwise we can ignore that variable. This one is slightly more complex. It is basically saying that we want to fix some variables, not all variables again, but we are not going to wait for all of them to be agree to that solution value. We can still fix certain variables to 1 if even if they are not set to 1 in all of these solutions. And on top of that, we can actually sometimes fix certain variables to 0 as well, right? So in let's say most of these solutions, that particular variable is set to 0, then its average will be pretty close to 0. In that case also, we can make a decision. Something where we cannot make a decision, it's when this probability is closer to 0.5. And the third one is that it is kind of similar to this approach, except that it is also taking the objective also into the account. Okay, so far we talked about how to predict solutions, but what to do if those solutions are not feasible. So again, in the literature, there are two approaches. One is that we can basically use local branching type of constraints. So it goes something like this. So if in the fixed solution, if the variable is set to 0, then we just add as it is. If it is set to 1, then we just add 1 minus x to it, where this j is when the variables are fixed to 1 in the solution, and this j is when variables are fixed to 0 in the solution. So basically it is saying how much we are deviating from the fixed solutions, and that should be less than equal to some eta. So this is a local branching constraint, and the idea is that we are allowed to move away from assignments which are kind of infeasible, but not by a lot. So this approach was used by Ding and others. The other approach is that we can let the solvers finish it. So the idea is that we have generated a partial solution or probably an infeasible solution. We can give that solution to the MILP solver as a hint, and let the solver finish it or fix it. So Skip particularly has this heuristic called complete solve heuristic, which basically can take a partial solution and try to basically finish it. So notice that we are never really trying to predict the values for continuous variables, because those are like the hardest values to predict. And even for the integer variables, these three approaches that we talked about, they basically focus on binary variables only. So this approach was taken by the other two papers, the one by Nair and Khalil. The next way in which machine learning can help the primal heuristic is by predicting better neighborhoods for a given solution. Again, there are a lot of people who have worked on this problem, and so there are lots of different approaches in which we can find high quality neighborhoods. The first approach is by Song and others in 2020. So they decided to learn partition of the integer variables into k disjoint subsets, right? So we have this bunch of integer variables, and then basically we want to partition them into some subsets. The goal behind all of this is that we just want to unfix one partition and keep all these other ones fixed to their values, and then find basically do an LNS over this unfixing. Once we are done with that, then we basically unfix the second one and keep all of the other ones fixed, and we basically iteratively repeat this process. So at the end of it, we might receive some of these solutions, so probably some good solution from this one, and so on and so forth, and evaluate what is the quality of all of these solutions, and that we can use for predicting better partition for these variables. So by doing all of this, we are basically trying to find some structure in our MIP. So we are trying to find which variables are closely related and how we can basically unfix those set of variables together. So it might improve this solution to a better quality solution. So the other approaches try to learn if the given variable is assigned to its optimal value or not. So in other words, they basically try to learn this kind of a probability. And so once we have learned this kind of a probability, we can use this for figuring out which variable to fix or which variable to unfix. So this approach was used by a lot of people. And in particular, we are going to talk about 3 of these papers. So first one is by Wu and others in 2021. So they used reinforcement learning to basically figure out which variable to fix or unfix. So in that sense, basically they will try to fix something and keep some variable unfixed and then see what was the observed solution and what is the quality of that improved solution. If that is very high, then this reinforcement learning agent will receive better rewards. Otherwise, it will receive bad rewards. The other approach is that let's say we are given this solution X and then we explicitly try to find the best solution that is eta unfixings away. Now eta can be some parameters, like this is basically kind of very similar to what we saw in local branching constraints. And so once we have this best solution, we can basically use this as a target to learn what variables to fix or unfix. So this approach was taken by Nicholas and others in 2021 and by Huang and others in 2023. So all of these approaches were actually compared against MIP solvers with its original default parameters, and it turns out that all of these approaches actually beat it, right? So they basically beat MIP solvers in their default setting. In fact, it turns out that even if you do not use any of these LNS heuristics and just simply try to use random fixings or unfixings, so even random, they also beat the MIP solvers in their default setting. So why this is happening? It's because typically a MIP solver has 2 objectives. So one is that we want to find a good quality solution. At the same time, we also want to prove its optimality, right? So the primal heuristics, they don't really care about proving optimality part, and therefore all of these approaches, if we just let it run for a while, then they can actually find better solutions than typical MIP solvers find in its default setting. Okay, so for the last part, we are going to talk about scheduling the existing heuristic. So the idea is that the MIP solver has a lot of heuristics inside it, and they are basically called at different times. So these different heuristics are effective on different families of MIP instances, and we just simply do not know which one are going to be most effective for a given instance or a given set of instances. Right, so basically these are treated as a multi-arm bandit problem. So let's say we have this bunch of arms, and for a given instance, let's say there is some probability distributions behind each of these arms. So when we pull this arm, we get some reward, and that reward comes from a fixed distribution. So we don't know that distribution, so we are just trying to predict it. So this setting basically is straight away applies to figuring out the heuristics itself. Right, so this arms themselves are, let's say, heuristics, and when we pull it down, we are basically calling that heuristic, and we are saying that you execute, and let's see whether you are successful or not. And based on if it is successful, then we will receive some reward. If it is not successful, then we'll not receive any reward, of course. And so the goal is that we want to figure it out a policy in which we want to pull these heuristics, right? So let's say initially, pulling out this heuristics will give us the most benefit. So then we'll pull out this heuristic first, this arm first, and later on, let's say some certain parts of the search, let's say this heuristic is more effective, then we'll start pulling this arm first, this arm now, and so on and so forth, right? So basically that's the goal for figuring out which heuristic to schedule when. And so a lot of this work actually I explained in ALNS. This was by Gregor Handel. So I have already recorded a detailed description of this heuristic. If you want, you can find it in the description and also maybe somewhere in the link above. And so the same idea is also extended by other people as well. So we are going to talk about Antonia. and others. So these people basically extended the same idea about ALNS, which is multi-arm bundled setting for figuring out which heuristic to execute. But instead of learning things for a single instance, they said that we are going to learn a prioritization order for a class of MIP. So they basically learn two things: priority and budget. So this is computational budget. And since they are learning things for a class of MILP problems, these two things are learned offline. So remember that ALNS was basically learning things online, whereas this work is basically learning this priority and budgets offline. But the overall idea is still the same. So still it's the multi-arm bundled kind of a setting, and we are still trying to figure it out which heuristic to execute when. So these people basically compared their approach against default skip, and obviously they managed to beat it. Not only they managed to beat the default skip version, but they've also managed to beat the tuned skip version, which is kind of very impressive. So this skip version, it was actually tuned for a particular MIP class, and this was also the MIP class in which for which this priority and budget was learned. And the last set of work that we want to talk about is by Khalil and others in 2017. So this is kind of a bit older work, but it is still kind of important to talk about it. So what these people did is that we have this branch and bound tree, and they said that we are going to learn a mapping from this to heuristics, right? So for each heuristic, whether for this node, whether they want to run it or not. And so that's what they want to learn. Now, the idea is that we only want to launch a heuristic if it is going to be successful. So that is one thing that's kind of very hard to learn. So we can basically solve this instance first with triggering heuristics on each node, and then figuring out whether the machine learning recommendation is to launch or not launch, and how good that machine learning recommendation would be if we actually launch it. So the training process already is kind of expensive. And also there is another problem. Let's say if we have the perfect knowledge of whether the heuristic will be successful or not on a given node. So let's say we are at this node and we are making a decision for a particular heuristic. And let's say we know that if it is going to be successful or not. Even in that case, this knowledge will not necessarily minimize the runtime. So that's what our goal is, right? And this can happen because if that heuristic was successful in finding a better solution, but that better solution was not a lot better, and the heuristic itself took quite a long to find that solution. So all of these things are kind of challenges in figuring out how to design the training process and how to design even the problem itself. So that's kind of a issue that is worth pointing out. Either ways, at the end of this work as well, they basically managed to figure out a nice setting in which they figured out how to schedule heuristics for a given set of MIPs, for a given class of MIPs. And for that, they can basically figure out a nice policy. We can basically predict whether certain heuristic will be successful on certain nodes or not. And based on machine learning recommendation, they would basically say that do not trigger these heuristics. And so therefore, the heuristic runtime would be less, and therefore the overall improvement in the primal integral would be much better. Okay, so in conclusion, we talked about machine learning for MIP heuristics, and particularly we talked about how we can use machine learning techniques to directly predict solutions for a given solution. How can we predict better neighborhoods, or rather which variables to fix or which variables to unfix, and a set of work which basically focus on existing MIP heuristics and just the scheduling part of it. So basically like which heuristic to schedule and how much to fix and how much to unfix and all of that part. So there are still like a lot of challenges remain in this work. So most of this work were basically for a class of MIP and not a generic MIP. So using this machine learning based solutions for generic MILP is still pretty hard problem. And so most of these works do not address that. Some of these works do, but not most of them. So that's kind of one big challenge to look into. So in this video, we only focused on the MIP heuristic parts, but this paper also talks about a lot of other components of MIP, which is particularly branching and cut selections and node selections and all of this. So I cannot fit all of them into a single video. So I'm going to create more videos for the same paper in which we will cover branching in one part and probably cut generation in the other part. So if you haven't subscribed already, please subscribe and hit the like button if you like this video, and see you in the next one.